speaking about lower bounds in more detail for tensors recently. So the floor is yours.
Well, thank you guys for joining me after lunch on the last day. Hope you guys are awake enough. Hopefully I can wake you guys up. So we're going to talk about fast matrix multiplication and in particular lower bounds. But I sort of just want to begin by hopefully briefly retelling the story that we've heard a couple of times so far this week. We begin in 1969. Strassen considered the multiplication of 2 by 2 matrices requires, well, it seems to, this classical algorithm requires 8 multiplications. And Strassen, I believe the story is set out to show that this was the best possible, but then managed to fail at that endeavor by finding a way of doing it in strictly fewer multiplications. And what's perhaps surprising about this is this data can be used to form an algorithm for fast matrix multiplication. As Olga told us, we can sort of imagine these A's and B's and M's and C's as all being capital letters and as sort of the quadrants of a large matrix. Suppose we want to multiply large matrices, we can divide it into quadrants, name the quadrants as the A's, the B's, and so forth, and use this to perform a recursive algorithm with only 7 half-size submultiplications as opposed to the usual 8. And this gives us an asymptotic speed up in the algorithm. So using that data, we've seen the analysis a couple of times so far this week. But so using this analysis, so Strassen, theorem, n by n matrix multiplication requires only O of n to the log 2 of 7 arithmetic operations, sort of applying this recursive algorithm with the data of that expression for that. And of course, the fact that this can be strictly smaller than 3 motivates a very natural definition. Strassen then defined the so-called exponent of matrix multiplication. So definition, omega exponent.
Can I make a picky comment?
Sure.
Because you said Strassen requires, you mean Strassen's algorithm. Otherwise, I would say it suffices.
Well, this is an upper bound. The big O means upper bound, right? So.
It requires just.
Sure. I would be wrong if I wrote that, right?
This about the algorithm. Strassen's algorithm requires. Then I agree.
Fair enough. So Strassen shows this is possible. Or we could say that, the circuit size is this size.
Big O of n to log 2 includes order of n squared.
It does. Exactly. It does. So this is not a lower bound result, but it is an upper bound result. And Strassen defines, the exponent as, sort of the natural thing. Let's just take the infimum over all the taus with this property, tau such that matrix multiplication n by n requires O of n to the tau, or maybe I should say there exists an algorithm. I don't think I'm wrong to say this. Okay.
Requires reminds me of lower bound, but you can say Franzen time.
But you also forgot inf. You said it, but you didn't write it. Omega equals.
Yes, thank you. Yes, take the infimum over all tau with this property. Now this is different than the way James defined omega on the first day, but in a moment I'll show that these two definitions are equivalent, or at least state the theorem that these two definitions are equivalent. So this is a problem in complexity. We're sort of bounding maybe the running time of some Turing machine, or really more precisely the size of some arithmetic circuit. I want to consider the arithmetic circuit model for matrix multiplication, count additions and multiplications and divisions. So that's why I use this phrase arithmetic operations. So this is a problem in complexity. It's not obvious that this should be a problem in linear algebra. But Strassen again sort of tells us that actually this problem of complexity, circuit complexity, really is in disguise a tensor decomposition problem. So I want to define the structure tensor of matrix multiplication, Mn, which I'll just define in bases, Cn by n tensor C n by, by n, tensor C n by n, which in bases is this. And you can sort of see the n squared dot products being formed here. And this is, if you want, this is, you can think of this as the, we're collecting together the terms in the dot product into the corresponding term of the result here. And with this sort of definition, this is the structure tensor of the endomorphism algebra, we have maybe the following reinterpretation of Strassen's algorithm. It's weird, my computer screen turned off. Is this on? It's not so critical that I actually show this, but maybe my computer's being weird. Something has gone wrong, I think.
Help is coming.
Well, help is coming, but it's okay. I mean, the only thing I wanted to emphasize was somehow my screen has also turned black, but if it's not working, it's not so important. It's fine. We'll come back to it. Mysterious problem. The only thing I wanted to point out is that the data of Strassen's algorithm, so the expression of the C, C11, C12, C21, C11 is a sum of 7 rank 1s. Well, it's just, slide data of Strassen algorithm is exactly, well, just an expression of M2 equals, and then I sort of collected the information of Strassen's algorithm to a plus da da da. So 7 terms here, each of which is a rank 1 and outer product of vectors of length 4, which maybe I can identify with 2 by 2 matrices. So Strassen's algorithm, the data describing it is just a length 7 decomposition of this tensor as a sum of rank 1s. And okay, so that motivates the definition of, well, maybe we should consider this as a notion of as a measure of complexity on not just this tensor, but maybe any tensor. So if T is, say, an A tensor, B tensor, C, well, we define the rank of T, well, is the smallest R, so that T is the sum of R rank 1 tensors. And the data of Strassen's algorithm is just the statement that the rank of the 2 by 2 matrix multiplication tensor is at most 7. And there's really nothing special about 2 by 2 matrix multiplication. We can imagine any, say, 10 by 10 or Q by Q matrix multiplication tensor. We could maybe get some information about its rank. Maybe we could find a rank decomposition. And we could then apply Strassen's recursive algorithm using this data. So instead of using, if we have a rank decomposition of a 10 by 10 matrix multiplication tensor, well, instead of dividing the big matrix into quadrants, we divide them into 10 by 10 subblocks. And with that, we can sort of maybe summarize this situation in the following statement. Maybe I'll call this Strassen's recursive algorithm. And it's just that, well, omega, which I define in terms of circuit size as like a complexity kind of thing, is at most log of Q of the rank of MQ, for any Q. So Strassen's recursive algorithm gives this result upper bound on circuit size. okay, well, I'm sort of concerned about this lower bound problem. So this is great for the question of finding algorithms. This tells me how to look for an algorithm. I just look for a rank decomposition of a matrix multiplication tensor. But I would really like to lower bound this. Luckily, Strassen also gives us the answer here. And Strassen says that, well, make sure I say it. So if there is an arithmetic circuit computing, say, n by n matrix multiplication using m multiplications, well, then the rank of the n by n matrix multiplication tensor is at most 2m. This is a result that Peter has alluded to. But this is sort of our link between going the other way. So Strassen's recursive algorithm gives us a link between tensor decomposition and circuit size in one way, and then Strassen gives us a construction. Essentially, this is the proof of this is due to a construction that turns a circuit into a rank decomposition. So we have, within a factor of 2, essentially equality here. This too, by the way, if this circuit uses only bilinear multiplications, in fact, it's equal to m, and then the 2 is to sort of account for the fact that maybe this circuit uses the commutativity of the variables. So maybe just to state it plainly, in other words, we could lower bound circuit complexity by lower bounding rank. So, okay, this is great. So we've reduced this problem of circuit size for matrix multiplication to a multilinear algebra tensor decomposition problem. But we've seen also that this particular problem is a little bit strange in the sense that, unlike for matrices, tensors of high rank can be approximated by tensors of low rank. And this is a little bit of a strange, sort of unpleasant situation. But we saw the example a couple of times that this E1 tensor, E1 tensor, E2, I think this was in maybe James' exercises or Peter's exercises, E1 tensor, E2 tensor, E1 plus E2 tensor, E1 tensor, E1. This tensor, I've written it down as a sum of 3 rank 1s, and in fact it does have rank 3. But there is a curve of rank 2s that approximate W arbitrarily well. So this is sort of causes a difficulty for lower bound techniques, because many lower bound techniques, if they show that a certain tensor has high rank, they're actually going to show that like a whole neighborhood of tensors around this tensor has high rank. So like any such technique could never detect the fact that this tensor has rank 3 as opposed to rank 2, because it has arbitrarily close tensors of rank 2 to it. But so what are they really seeing? They're really detecting an auxiliary notion. So in some sense, I want to define an auxiliary notion of rank, which I'll call border rank, which I sort of, define away the problem. So I'm going to make a new definition. The border rank of T, is the smallest R so that, T is approximated by tensor. And maybe I'll be more precise to say a limit of tensors of rank R. So many rank lower bound techniques are actually border rank lower bound techniques, which you might think of as bad news until you consider the following fact. Maybe I'll write a theorem that sort of summarizes the state of play so far. The following are equal. So infimum tau such that n by n matrix multiplication requires O n to the tau arithmetic operations. 2 infimum tau such that the rank of mn is O of n to the tau. These are equal. 1 is equal to 2 due to the two Strassen theorems. We have 1 is lesser or equal to 2 because of this, and we have 2 is lesser or equal to 1 because of this. And well, luckily, Bini sort of gives us a third thing here, infimum over tau, such that the border rank of matrix multiplication is O of n to the tau. So Strassen gives us that it's sort of enough to consider tensor rank when considering the exponent of matrix multiplication. Bini tells us that, well, it's similarly enough to consider border rank. So that will be the name of the game today. I'm going to look for techniques to lower bound border rank, which in view of this result is sort of enough. We're not sort of throwing any possibility away in terms of lower bounding omega.
Can I ask a quick question?
Yeah.
So does this mean, like, related to the fact that the tensor ranks are lower circuits, does this mean the actual rank and the border rank are always the same up to a constant or something? Asymptotically or something?
Well, asymptotically, yeah. They're the same in exactly this sense. And we can be more precise if we do the exercise that Peter gave us, where that would sort of bound how different the rank can be compared to the border rank. But it is a fact that at least in the sense of taking infimum and sort of considering very large, there is no gain to be made.
Oh yeah, then I understand. You're clearly defining it. Yeah. I
This is basically saying, I can completely
You're
rate.
basically stating what I just asked. Yeah. Exactly.
Right.
Is this equivalent something special about the matrix multiplication tensor, or is it true for some general?
It's true for general tensor that the asymptotic rank, if I define it in terms of rank and in terms of border rank, are going to be the same. And the thing that's special for matrix multiplication is that it has this sort of self-reproducing property that if I take a Kronecker product of two matrix multiplications, I get another one. So that sort of makes the statement very clean. But this might show up in general as a statement about the asymptotic rank. You could define it in terms of rank, and it will still, you won't have a new notion if you use border rank instead. Okay. And of course, if we lower bound border rank, we also get a lower bound for rank, because border rank, just an observation, has to be at most, or at least at most of the rank. So let's jump into some lower bounds. So the first idea for lower bounds is just the simple observation that, well, maybe tensor rank and border rank are hard, but matrix rank is easy. And we have, for instance, very fast algorithms to compute matrix rank. So one thing we can look for look for, say, a flattening map, which will be the following. I'm going to look for, it'll have domain the space of all tensors, and it'll go into a space of matrices. And I want F to be linear, and F to map rank 1 to low rank matrices, to say rank, say less or equal to K matrices. So if I can cook up such a computational gadget, what can I do with this? Let's consider the following. So suppose T is rank at most R. Maybe I have a rank R decomposition for it. Well, let me apply my flattening map and use linearity. So the f of t is f of A1 tensor, B1 tensor, C1 plus plus f of AR tensor, BR tensor, CR. And by assumption, all of these images of rank 1s have low rank. They have rank at most k. So the rank of this result is at most kr. So rank, if I take ranks of both sides, so rank of f of t is at most kr. So just sort of summarizing what we've observed here, given this situation, well, rank of T less or equal to R implies the rank, just the ordinary matrix rank here of the flattening of T is at most K R. And maybe I can sort of write the contrapositive of this statement. So that means that the rank of F of T strictly bigger than K R implies the rank of T strictly bigger than R. Maybe another way of writing that is to simply say that the rank of T is bigger than or equal to the rank of F of T divided by K. Okay, so this gives us, so this is sort of the mechanism by which the rank can be lower bounded. And then we can furthermore observe that, well, this lower bound has the property that I mentioned earlier, that if it shows that a certain T has high rank, it's actually going to show the same for all T in a neighborhood of that. Just in view of the fact that matrix rank is semi-continuous. If the matrix rank of something is high, then that's also true of everything in a neighborhood. So actually we get a border rank lower bound using this flattening technique. Okay. Well, so then what's the name of the game? Then the game is to look for such data. How can we do that? The very first kind is maybe the very first thing we should consider is, consider, well, F from A tensor B tensor C to, well, I'll write it suggestively like this, A tensor B tensor C. So this is a matrix space. I'm just sort of by force thinking about the second two factors as being just one factor. If you're a little bit uncomfortable with this, we can imagine that there's a canonical isomorphism with where I sort of make very explicit the this. So maybe if you prefer this way of thinking about matrices as linear maps, this is the actual linear map that I'm wanting to talk about. And I will just, as a matter of language, I will say that T is mapped to T sub A. And then, okay, so this is a map from the whole tensor space to a space of matrices. It is a linear map. I just need to ask, well, what matrix rank do I flatten a rank 1 tensor to? So let me consider a rank 1 tensor like A tensor B tensor C. Well, what does it go to? It goes to A tensor B tensor C. What is the rank of the, what's up?
Not forward, not right lower.
Okay. Is this okay?
The other forward, you can go all the way to the right.
Okay, sure. And this is a matrix now. What rank is it? It's 1. Yeah, this is just an outer product. So K is 1 in this example. So that means that, so I'm not supposed to write over there. I'll come over here. That means that applying this sort of principle to this particular flattening, that the border rank of T is at least the rank of T A. Okay. So this is good to know. This is also sort of underlies the definition of minimal border rank for concise tensors, but that's not so important for me to talk about now, but it is due to this principle here. And so what does this tell us about matrix multiplication? It tells us that matrix multiplication has this flattening full rank in each of the three directions. So for matrix multiplication, say n by n, this flattening is a matrix that's like an n squared by n to the fourth matrix. And it's full rank, so it's rank n squared. So we get the border rank of mn is at least n squared. Okay. Hopefully this is not, news to anybody. Let's go further. How do we go further? Well, okay, let's look for a different flattening method, which are, I guess, equivalent to Strassen's equations. But I want to sort of write them in a suggestive way, and it is an explicit flattening. And well, the flattening here is going to be, I have to take tensors, and I'm going to come over to, well, a space of matrices. And what is it going to be? It's going to be A tensor B dual maps to wedge 2 A tensor C. And maybe I should sort of, well, name what this is. I'm going to call this T wedge 1 sub A. But in case it's not 100% clear what the image of this is, let's sort of build it up step by step. Thank you.
On the right-hand side is also C.
There's a C here, B dual here, A, and A there. Is this okay?
Yeah, okay. Doesn't look like a C. It looks like a... That
Is that okay? Thank you.
parenthesis missing.
I see. I'm trying to improve my handwriting, so I appreciate the feedback. So how do we construct this image here? Well, we have, first I'm going to take the ordinary flattening, TB, from B dual to A tensor C. First step of the construction. Then I'm going to take the Kronecker product of this matrix with the identity map in A. So I'm going to take the identity matrix in A, Kronecker. I guess Kronecker is written with like a box times here T B. This is from A tensor B dual to A tensor C. And then as the last thing, I want to post-compose this map with just the wedge map on these two factors here. So then, post-compose with like wedge tensor identity or something, identity on C to get. So basically, I take this down to wedge 2 A tensor C to get, well, so the whole map here is then T, what I call T1A. Okay. Why is this doing anything for me? Well, I indeed have at least a linear map into a space of matrices. Second question is, what is the matrix rank of the image of a rank 1 tensor? So let's let A1 tensor, B1 tensor, C1, and I want to consider this, and I want to compute the rank of this as a matrix. So maybe I want to compute the dimension of the image. So maybe I'll apply it, see what it does to some element in A tensor beta. This is a rank 1 element of the domain that's a spanning subset of the domain, but it's one that's particularly convenient to compute the image of. And well, what do I get? Well, I get, I think, beta of B1, and then, well, this A just comes along for a ride until I wedge it with A1 at the end, so I get A wedge A1 tensor C1. Okay. And the thing I want to observe is that this is an element of just of the whole space A wedge A1 tensor C1. So any rank 1 maps inside of this, so in particular any linear combination of rank 1s, in fact every matrix maps inside of this subspace.
I know what you mean, but the notation is confusing. I mean, you define T goes to T index A super this wedge something, and now here it's like confused. Or is no? Or why is there a T?
So
T is.
So I'm just wanting to.
The notation is not consistent, and so maybe.
Is it not? Well,
people.
I'm just wanting to name.
Yeah,
the
this
flattening.
naming is not what you use.
I think it is what I use, right? So I'm flattening this
The
tensor.
subscript should be A, not C.
Subscript should be A.
Oh, excuse me. Thank you.
Maybe
This is okay now, yeah. Thank you for that. Okay, now, so I'm just wanting to flatten this rank 1 and apply it to a rank 1 matrix there. So what is the dimension of this image? Well, I get essentially all of A here, except I'm wedging with A1. So I can only get the stuff that's like, maybe if I extend A1 to a basis, I can only get the span of like A2 up to A here, wedge A1. And basically this A1 kills any contribution of A here. So what I'm wanting to suggest is that the dimension of this is dim A minus 1. Which is good for me because this thing is occurring in the denominator of my lower bound. So sort of the mechanism, the point of doing this wedge product is to sort of get this minus 1 here. I'm making the rank 1 tensor map to a lower rank matrix by 1 than if I did not include this last step here. Okay. So what can we get with this?
You are now solving one of JM's exercises, right?
I guess I'm solving one of JM, but there's.
It's good that we do.
Yes. I did not know JM was going to make this an exercise before we got to it. But so let's apply Strassen's equations. Apply this flattening to see what we can get for 2 by 2 matrix multiplication. Well, so 2 by 2 matrix multiplication. Maybe I'll write it in sort of a. I'll write it out as a tensor. So this is 1 1 1 1 1 2 2 1 2 2 1 1 1 2 2 1 2 2 x 1 1 So you can check for each of these, like x1 2 times a 2 1 gives me a contribution in 1 1, and that's sort of how this is being constructed here. So this is a tensor in C4, tensor C4, tensor C4. I want to modify this slightly. I want to restrict this to a new tensor S. So restrict to S and C3 tensor C4 tensor C4, where S is x1, x3, x2, x1 plus x3, x1, x3, x2. So I've just sort of let all of my x22s be. I did because I did. Because I wanted to be clear that this is the matrix multiplication tensor, but now I'm assigning x1 to be, I'm assigning x11 to be x1, x21 to be x3, x12 to be x2, and then x22 to be x1 plus x3. So this is a restriction of that. And as Peter showed us, we have an inequality on border rank when we restrict. Thank you. So as Peter showed us, well, M2 restricts to S implies that the border rank of M2 is bigger than or equal to the border rank of S. And we're going to apply Strassen's equations to S here. And so since this is our maybe first non-trivial example of a flattening, I will write the flattening map. So S wedge 1 A. What's going to be a block matrix here, minus x2, x1, 0, minus x3, 0, x1, minus x3, x2, where x1, x2, x3 are these 4 by 4 matrices coming from, well, maybe I'll write x1 is 1, 1, 1, 1, x2 is 1, 1, and x3 is 1, 1, 1, 1. our 4x4 matrix. So this is a 12 by 12 matrix. And I've chosen the restriction such that this 12 by 12 matrix is full rank. I sort of played around with the restriction a little bit until I got the rank of the flattening to be as big as possible. In other words, we get the biggest lower bound possible. So this rank of this flattening here is 12. So then what lower bound do we get? Well, we get the border rank of S is at least, well, the rank of this, S wedge 1 A divided by 2. This 2 is the dimension of the first factor minus 1. Remember, we get this minus 1, so 3 minus 1 is 2, which is 12 divided by 2, 6. Okay, so we've improved our lower bound from 4 to 6. We have not met Strassen's algorithm yet, but we do have some more information now about the border rank of 2 by 2 matrix multiplication. Okay. Similarly, we can apply the same idea to, say, the 3 by 3 matrix multiplication tensor. So apply the same idea to M3. First restrict.
May I ask a question?
Yep.
So first, we started with the matrix multiplication tensor.
Yep.
Made the distinction to S. So then we are in dimensional with 3, 4, 4, and then we apply the flattening.
That's correct.
Right. Because otherwise there wouldn't be a 1/2.
That's exactly right. And maybe that accounts for why I want. So I want to make this restriction because if I don't restrict, I have a 3 in the denominator here.
Can you tell me that these X matrices that you wrote there, what is it?
Those are maybe S of alpha 1, S of x1 is that. X2 is S of alpha 2. I'm just plugging in the 1 for x1 and 0 for the rest.
Alpha 1, alpha 2 are like standard base.
Yeah, I guess the base is dual to the x's.
Okay.
So yeah, it turns out that Strassen's equations work best when this is 3. And if I have time, I'll explain why that's the case. But basically just because this 2 is better than 3. So even though maybe I get a slightly smaller rank here because I have a smaller matrix here, I'm compensated for that by the fact that I have a smaller denominator here. And just the balance of those two factors works out to where I do want to do this restriction. And I do the same thing for M3. I take a restriction to C3, C9, C9, where I need to take the restriction generic enough. Basically, you can take a random restriction. And it turns out you can get the full rank flattening there to get flattening rank. Well, 3 times 9 squared. Excuse me, 3 times 3 squared equals 27. So we get that the border rank of M3, well, it's again bigger than this border rank of this generic restriction, is bigger than or equal to 27 over 2. Well, 27 over 2 is 13.5. So if I'm an integer that's bigger than 13.5, I'm really bigger than the ceiling of it, which is 14. So I get a lower bound of 14 for 3 by 3 matrix multiplication using Strassen's equations. So we can generalize this idea of Strassen's equations. And by the way, what time do I finish? Do I finish like 30?
Past the hour.
Great. Okay. So we can generalize to Koszul flattenings. And well, the idea is very similar to Strassen's equations. A tensor B tensor C maps to Well, wedge PA tensor B dual to wedge P plus 1 A tensor C. And the construction is essentially the same construction. By the way, I will name the result of this flattening. I will call this T wedge P sub A. And, well, how is it constructed? It's T, I flatten it in the B direction. I take the, so T wedge P A is, well, I take T, flatten it in the B direction. I take the Kronecker product with the identity matrix in the wedge PA direction, and then I post-compose with like wedge tensor identity on C, if you want. We sort of do the same sort of three-step process, but we are our little our A from the tensor gets wedged with our A from the tensor gets wedged with a lambda PA from the input to give us a lambda P plus 1 of A. So this is TA wedge P. And okay, well, we should ask the question, this is a linear map from a space of tensors to a space of matrices. What rank does a rank 1 tensor go to? So again, A1 tensor, B1 tensor, C1, I'm going to take the wedge P sub A, and I'm going to apply this to something sufficiently simple to evaluate. Maybe we'll call omega my term in wedge P of A tensor beta. Well, what am I getting? I'm getting beta on B1 times omega wedge A1 tensor C1. Similar to before, then I ask, well, what is the dimension of this? Well, the only term, this is a scalar, this is a single vector. It's just coming along for the ride. So I just need to ask, what dimension of thing, what space can I get here when I wedge an arbitrary P form with a specific A1 vector? Well, this is going to live inside of, maybe I'll call it wedge P of A. So that's my lambda wedge A1 tensor C1. And in particular, the only forms that sort of can survive here being wedged with a basis vector are not all P plus 1 of them, but dimension A minus 1 choose P of them. So this is dimension, this space of this image is dimension, parenthesis. I'm not sure. Sorry? Okay. I'm writing a binomial coefficient here. So we can apply this. What if we apply this to matrix multiplication? We cannot, with Koszul flattenings, make an improvement for 2 by 2 matrix multiplication anymore. There's nothing better than Strassen's equations.
Sorry, can I maybe interrupt that formula? Like, if A1 was just a zeta basis, then does like all subsets of basis vectors that are the same as that basis?
Exactly right. Yeah, maybe the easiest way would be to say, imagine a basis of A that has A1 as one of the basis vectors. Then the only terms that are allowed here are A1 wedge stuff with only A2 through A, dim A. And how much?
Different, I guess.
Exactly right. Exactly. So what survives is only, so we get a minus 1 here because we're sort of removing the possibility of having, like A1 has to be there, so we sort of, that's accounted for in the minus 1. So we can use this to get lower bounds. And indeed, if we say take S generic, say S in C5 tensor C9 tensor C9 generic restriction of M3 in the first factor, and then I apply P equals 2 Koszul. We get, well, what is the size of this flattening? It's a 90 by 90 matrix, and we compute its rank, and we get a full rank. Get full rank 90 by 90 matrix. So what do we get? We get the border rank of M3 is more than the border rank of S, which is at least 90 divided by, well, dim A minus 1 choose 2, so 4 choose 2. So 4 choose 2, which is 6. So 90 divided by 6, 15. Yay, so we improved by 1. So Strassen's equations give us 14. We can improve by 1 to get 15. This result is due to Landsberg and Ottaviani in 2013. And they show that with Koszul flattenings, it's possible to give a result for all n. So theorem Landsberg. The border rank of n by n is bigger than or equal to 2n squared minus n. And I think if we plug in n equals 3, we'll get our 15. N equals 3 is 18 minus 3 is 15.
Yeah, Austin, can I ask a question? Like,
Yeah.
just a big picture thing. You're proving lower bounds for like concrete small tensors.
That's right.
Are there black box techniques that go from these lower bounds to proving things like this for all n? Or is it some of the techniques generalized to all n, some do not?
That's an excellent question. So to what extent can we apply these techniques for all n? Well, for concrete small n, the method is essentially completely automatic. We can just press a button on the computer and get a lower bound. And that's just a convenient tool. But yes, to pass to like an infinite sequence of tensors here, there's nothing about the tool that prevents me from applying it there, but we have to do some theoretical work to make it work.
Okay.
And indeed, so maybe I can just, so the Landsberg and Ottaviani in this article, well, it's P equals n minus 1 Koszul flattenings. No restriction needed. So basically, they consider the flattening as some big matrix, but they sort of analyze the combinatorial structure of this matrix, and sort of, by working very hard, they are able to show that it has whatever rank performance it needs to get this theorem. So it takes some work to do it for an infinite sequence, but it can be done.
It doesn't have full rank.
Oh, yeah, sorry.
Yes, that's right. It's not the rank enough to get this, and in fact, I think for this particular flattening, it's not full rank. In fact, this is one I just did on my computer preparing for the lecture today. But this theorem says, actually no, it's correct. So 2 is p n minus 1 in this case. But in general, I don't think these flattenings are full rank, but they're precisely the rank needed to give this down there. Question?
I mean, can you say anything about the intuition about these constructions, or I mean, how do you?
Okay, excellent question.
I mean, Strassen had his equations, I know that, but then this interpretation with the Koszul flattening came later. So
That's true.
It comes from somewhere.
Okay.
I know.
So-
I'm surprised to see this. Now I know it, but why?
So maybe I will pick one way of answering this question. And, well, one thing that is true about the Koszul flattenings, all of them, is that we can consider everything in sight as a GLA, GLB, GLC module. So we can consider a big symmetry group, G equals GLA times GLB times GLC module. We can consider everything in sight to be this. And these flattenings happen to be, they don't have to be from just the way the method works, but they happen to be equivariate maps under this. And this means, for instance, that this statement that, say, all...
So somehow your linear map F that you use, then you would say maybe I would like to have some equivariance property, and then there are not so many possibilities anymore. Maybe it's this?
Precisely, yeah. It makes sense to insist, although it's not required from the method.
That's maybe JM knows.
So we had no idea this was going to be linear. We basically tried all possible equivariant maps, and this one was the best one we found.
But the equivariance guided you.
Yes. So
Yes.
then you have a finite list
Okay.
for any given dimension.
That's an answer.
And I guess it was after the fact that you discovered that the p equals 1 was essentially equivalent to the Strassen's equations?
Yeah, that was actually much later.
Okay, that was much later.
And it's not equivalent, actually, it's slightly smaller.
Okay, okay.
That's another lecture.
But I think that's probably the best sort of explanation of why we might look for these. In fact, the flattening method is also very prevalent in even the polynomial complexity, like the polynomial Waring problem. People would like to lower bound like the Waring border rank of polynomials, and the so-called Young flattenings are essentially the same idea. You look for maps from the ring of homogeneous polynomials to matrices with the same properties that we look for, and you can do like a systematic search over equivariant maps to sort of consider the space. Okay.
You know it's not worth considering non-equivariant maps?
Well, it's just that rank and border rank are both invariant in this group. So, I mean, I guess it's very unclear where you would look for that. But, you know, yeah, it's unclear how you would look for such a flattening. But, you know, it sort of makes a lot of sense to insist that it's. Yeah.
Well, if you have a variety that's invariant under group action, it's ideal that the set of all polynomials vanishing on it will be invariant under the action of the same group. What we are looking for are polynomials in the ideal of a set that's invariant under changeable bases. So it's natural to look for sets of polynomials, because we have a collection of minors. That set is also invariant under the changeable bases, because you know ultimately if you're finding the correct answer, it will take that form.
But it's natural, and you're saying it's a complete approach. There's no need to look at other polynomials. Or you're just saying it's natural.
It is, if you wanted to find all polynomials, you would need to use some kind of invariance. If you want to find one polynomial a priori, there could be another method, but no one has found one yet.
So maybe I want to say just a little bit about the power of this method. Well, so the power of this method depends on two numbers. It depends on the maximum rank that I can get from the flattening, and it depends on the denominator here. So the size of the flattening, if say T is in CA tensor CB tensor CC, well, flattening, say the P flattening is A choose P, B by A choose P plus 1 C matrix. So being most optimistic, this thing is full rank. It has rank the smaller of these two dimensions. So the best bound I can show is, so best bound, just from the numerics is, well, the smaller of A choose P, B, A choose P plus 1 C, divided by, well, my A minus 1 choose P, divided by this denominator of the rank of the flattening of the rank 1. And if we sort of expand this out and simplify it a little bit, this just equals the smaller of A over A minus P times B, A over P plus 1 times C. And if we consider that we're trying to lower bound the border ranks of, say, square tensors, where in particular B equals C equals M, well, then this is best when when A equals 2P plus 1, and bound is 2P, and the best bound is 2P plus 1 divided by P plus 1, M is less or equal to 2M. So by the way, this explains why I wanted to take a generic restriction to 3 in the case of Strassen's equations and 5 in the case of the P equals 2 Koszul flattening. But this is, a bad news result, at least for this particular class of flattenings. It says that they can never show a border rank lower bound better than 2M, none of them. And you could ask, well, could any other flattening idea, do better than this? And the answer is not much. And if I had more time, I could explain why not much. But I will just, barrier any flattening, can not prove a bound better than 6m.
Maybe going to be at least the initials of the authors of that paper. Is it through
So I learned the
EOW?
okay, EGOW. I learned this from the proof of this from Visu McCom, and he probably learned it from Avi Victorson. Like, I guess that's the W, right? Okay, perfect. And as Jay mentioned, maybe this 6 is even too optimistic here. Maybe it's really something like 2. Yeah. Oh. O is other.
It's okay.
And this is horrible. And why is this horrible? It's because, well, we can just by dimension count ask what is the rank of or border rank of a random tensor. So consider random, T in C M tensor C M tensor C M B random. Well, by dimension count, I'm trying to write it as a sum of R rank 1s. Well, what's the dimension of a rank 1? Well, it's like 3 choices of M numbers. So there's 3 M rank 1s. And how many tensors are there? Well, there's maybe -2, I guess, if we want to. What was that? That's true. So it's a 3 minus 2, and then M cubed. So random tensor has rank equals border rank equals this number, and this is something like, well, M squared over 3. Oh, sure. Yes, that's true. So, but just, I'm looking to say what the order of this number is. It's something like the square of this. But our lower bound technique, and in fact, any flattening lower bound technique can't do better than linear in M. And it would, and I can even say more, that there is no tensor that we have an example of that is explicit in a precise computer theoretic sense, for which we know it has even a superlinear provable lower bound on rank. So forget matrix multiplication, forget this. We can't even solve the so-called hay in a haystack problem. A random tensor, like we've got all this hay here, tensors of rank m squared, but we can't see any of them that have superlinear rank, even superlinear. It's frustrating. Yeah. So, yes. So I will, and certainly flattenings can't do it for us, just we have a barrier result. And so maybe I'll end with this bad news, but in 30 minutes we will, I don't know, try to improve the situation a little bit.
You cannot find explicit tensors with ranks at 6m, that's what you mean?
We cannot find explicit tensors where we can be 100% sure by proof that its rank is even more than 2m. And I think
2.03.
So Landsberg with Mihalik they with great effort found a 2.03m rank tensor.
Sequence.
Sure, m, for any m, and this was a incredible breakthrough, breaking through the 2m barrier, but still, it shows the state of the problem.
Most depressing theorem I ever heard.
Sure.
Okay, let's thank our speaker. Time for 1 or 2 quick questions.
I mean, so like as someone who doesn't know any algebra,